All right, hello everyone, and welcome to my final project presentation. My name is Matt Gossett, and my final project is on the LibRecommender algorithm. So to introduce everyone to LibRecommender, it's a powerful recommender system that enables users to train, test, evaluate, serve a lot of different algorithms with a range of different frameworks. What's really cool about LibRecommender is that it's a singular API, but it takes algorithms and backend frameworks from different types of recommender systems within Python. So I really enjoy working with this project, and I'm excited to show you all how I used it. But here first are a couple of links to the website and GitHub repositories, so you can take a look for yourself in a little more detail. And I'm going to move on to the problem statement. So the challenge with recommender systems, as we think back to using the movie ratings data set in assignment 6, is that it can be very challenging to create a network model, a graph network, for example, to build a recommender system. It can be a challenge to compare a system built in PyTorch to a system built in TensorFlow, and to quickly iterate or update parameters or add new data or make predictions or recommendations for new items and new users. So a lot of challenges with the complexity of recommender systems. But the great thing about LibRecommender is that it's relatively quick and easy to work with, and it's also effective at making recommendations. So one thing that's really cool is that it will actually pull algorithms with different backend frameworks from PyTorch, TensorFlow, Python, DGL. So all these different frameworks, and put them in a singular API experience so that you can iterate and actually evaluate models within those frameworks on the same data really at the same time. So just to kind of reiterate what the technology does, like I said, implements a lot of different algorithms. It has both collaborative filtering and content-based filtering recommendations. So collaborative being looking at recommendations based off similar user profiles or user ratings, and content-based being make recommendations off of your, the items that you've rated and the attributes of those items. So that's kind of the difference there. It's relatively low in memory, so compared to some of the other larger algorithms or models out there, I was able to run this in my demonstration I'll show in just a second with a relatively large 1.5 million data set and get results back in just over an hour with the GPU, whereas I know some larger data sets like that could take longer in some frameworks. So relatively low memory usage. Able to train on either explicit or implicit data sets. So whether you're using a preloaded data set or you're actually generating new data within the model and within the code itself, you can generate recommendations off of that. It's an end-to-end framework, so you can prepare the data, train the model, evaluate the model, save the model, load it, serve it. So really you can do everything within this one LibRecommender framework, which is pretty cool. You can make cold start predictions, recommendations. So if you have a new user, you can make recommendations for that new user based off of either average recommendations or popular popular preferences amongst the user base. And so that's really cool. Something that's definitely needed with algorithms is how do you handle new users, new items, and for new items it will actually be able to similar to new users taking the average, it'll kind of aggregate the existing items and come up with predictions and recommendations for those new items. The has the ability to use dynamic features and sequence. You have a unified API, and it's easy to retrain and add new users and new items and new data sources. So that's great too. So getting into this demonstration, I've used this beer ratings data set. There's a 1.5 million data points here. We have 45,000 different beers, 33,000 users, 5,000 breweries, 100 plus styles. We have different ratings for aroma, appearance, palate, taste, overall attributes, like I just said, brewery, time, style, name. Here I got a summary table, so you can kind of see, the beers are all rated on a range from 1 to 5, with 5 being the highest, 1 being the lowest. And we just have an idea here based off the counts and the quantiles of where these ranges are falling. So jumping ahead here, the first model I'm going to talk about is LibGCN, which is a collaborative filtering model with a PyTorch backend, similar to the convolutional model we worked with in this course. But you'll see in a second that the ability to create this model is relatively simple compared to some of what we've done already. So the first part of this is just creating the initial data set. And in order to do that, there are 4 required columns: user, item, label, time. So basically all I did was extract this data. I converted user to numeric, which is necessary, and then these columns have to be in order, but basically just rename the columns. And here I use the overall review or overall rating as the label, so it would make predictions based off of that. Then you can see in the bottom section here, I split the code into 80-10-10 for train, validate, test. So that was super easy to get that back. Next, creating the actual model. So in LibGCN, there's a few different parameters you have for embedding size, number of epochs, learning rate, batch size, number of negatives, device. So in total, there's not a lot of complexity here as far as creating the model. There's a few parameters you can play around with to see what makes sense for your model, but overall, super simple to create a model. And then as far as fitting it, evaluating it, you can use different loss metrics. So evaluation metrics, you can use loss, AUC, precision, recall, and DCG, and these allow you to evaluate, if you're playing with the different parameters, what's working best as far as your model results. Now here I'm going to show what some predictions or recommendations look like. So what I did here was I found one user, 119, that just had a few, not too many ratings, so we can really kind of dial in on what this user liked. And we see in green here, they like the American IPA style beer with giving an overall rating of 5. And then that one in the red on the bottom, the wit beer style, they gave it a rating of 3. So my hypothesis was anything, IPA, American IPA, they probably rate highly. Wit beer, they probably rate lowly. So we want to really make sure the predictions, the recommendations align to that. What I found was I pulled out an American IPA beer 10784 in this bottom left, and it rated it at 0.83. So this is the recommendations coming out at a scale of 0 to 1. 0.83 is quite high, so happy with that. The wit beer that I found, 41801, came out to a recommendation of 0.54, so kind of middle range, which made sense based off the 3 rating that the user gave above. So overall, I'm really happy with this. The cold start prediction for a new item, it gave it a rating of 0.56, which seemed a little conservative based off some of the higher ratings for this user, but overall, I'm happy with the conservative recommendation or the conservative prediction on a new item. I think makes a lot of sense. And then as far as the recommendations go, so you can specify the number of recommendations you want to get back. Here on the bottom right, you can see I specified 7, so I got back 7 recommendations, and I can actually see what different styles I recommended. In this case, it was some ales, stouts, and then I can actually even make recommendations on a new user, and I can specify recommend some popular beers for this new user, and it recommended 7 beers. You can see they're all quite popular. They had all over 1,000 ratings, which is really high, and they're rated highly. So overall, I was really happy with the way the predictions and the recommendations worked out. Now I'm going to talk about this YouTube ranking model. So the YouTube ranking model is a content-based recommendation with a TensorFlow backend. The idea behind this is that you can actually input different features, so numeric, categorical features into the model to make it even more more customized and make better predictions, better recommendations. So similar here, setting up the data, 4 required columns, user item label time. So had all 4 of those columns in this initial setup. And then I have 2 numeric features, review aroma, review appearance, that I added into the model, as well as 1 categorical variable, which was style. So what I did here was I just created dummy variables with 0, 0, 1, hot, 1 hot encoded, to represent, a 1 if the beer is that style, or 0 if it's not, and I use that in order to inform the recommendations. So splitting or creating the model inputs, you can see in this upper section here, there's a few required variables. The first one is sparse call. So sparse call is the categorical features, in this case all the styles. So you make a list of all those styles, and that's your sparse call. Dense call is the numeric features. So in this case, I just had 2, but again, create a list, and that's your dense call variable. User call, I didn't in this case have any user descriptive features, but if I did, add gender, any demographic data, or any other thing I would have put that in the user call list. And then item call, I put all the features, both numeric and categorical, in the item call variable, because that is all the features describing an item. And the only requirement here is that those 2 equal each other, sparse call plus dense call. So you must have all of those in either user or item, which is why those 2 equal each other. You can run a assert function to make sure that's the case. Now splitting the data, exact same thing, 80-10-10, and then creating the model. Really similar look and feel to LightGCN. This is where you can highlight the fact that this was a TensorFlow backend versus a LightGCN as a PyTorch backend, and you get the same API experience between the 2, which is really great. And again, looking at this recommendations and predictions for user 119, we see the predictions for they really like the IPA, so we wanted to see what would it be for an IPA versus a whip beer. The whip beer recommendation that I came up with was 106.49, and it spit out a 0.11, so even lower than the LightGCN, which I think having those additional style features probably weighted it down some, which I liked. And then the American IPA 107.84, it came out with a 0.88, so even higher than the LightGCN. So a little more of the 2 extremes, but I liked the ability to distinguish between these styles and really give specific recommendations. I didn't quite get the new item prediction that I was expecting as close to 0, but didn't quite figure that one out, but kind of parking lot that one for now. The recommendations that came up with for 119 made sense to me. I see the ales, which aligned with their preferences, and then for the new user, again, we just see like popular beers with over 1,000 ratings, all pretty much 4 and above. So overall, I was really happy with the recommendations here as well. So in conclusion, pros of LibRecommender: it's easy to implement, covers a wide range of algorithms, end-to-end framework. Just thinking back to assignment 6, I have to think that this is one of the better ways to implement a recommender system with deep learning. Just the ability to update parameters and switch between algorithms and test out new ways of making predictions and recommendations. It's super easy to get up and running with the data that you have. Cons: so there's a limited set of algorithms. Obviously, any algorithms that's not supported by LibRecommender, you'd have to work with outside of this framework. But so that's one consideration. Then, of course, it doesn't require a super deep understanding of each framework. I was able to, get the YouTube recommender, ranking recommender up and running without knowing super detail about all the parameters or all the back end. So potentially you could run into some risk there if you don't understand fully what you're working with. But overall, I was really happy with this and really happy with this course, and just want to thank you all for listening in. And yeah, I hope you all have a great rest of your day. Thank you so much.